Stephen Hawking died earlier this year on the 14th of March. As a student in the 1960s, he was diagnosed with motor neurone disease and given just 2 years to live. But confounding all expectations, he lived to become the most famous scientist in the world since Albert Einstein. His incredible determination and drive to succeed despite any obstacle should be an inspiration to all of us. We should also remember his incredible communication skills and his lifelong commitment to those less able and less fortunate than himself. Hawking's research was critical to establishing our modern understanding of black holes. When he began his investigation into their properties, they belonged to the outer fringes of acceptable science, but Hawking lived to see overwhelming evidence established for their existence. We now know that a supermassive black hole of about 4 million times the mass of the Sun inhabits the central region of our galaxy, and it's believed that a monster such as this exists at the centre of all galaxies. The LIGO gravitational wave detector in the United States discovered the first ever gravitational wave signal in 2015. This was produced by the collision and merger of two black holes in a distant region of the galaxy. Since this time, several other gravitational wave signals have been detected. Much can be deduced from gravitational wave signals. We know the black holes whose collision produced the first signal had 29 and 36 solar masses, and they coalesced into a rapidly spinning black hole of 62 solar masses. Now this might sound rather odd, as 29 plus 36 equals 65, so 3 times the mass of the Sun seems to have disappeared in the process. In fact, this mass was converted into pure energy in the form of gravitational waves in a remarkable instance of Einstein's famous formula E equals mc squared, where E is energy, m is mass, and c is a constant, the speed of light. Einstein's formula implies that mass is just another form of energy, and as energy is conserved in all processes, any change in mass has to be taken into account when we balance the books. Still, you might say, black holes are supposed to be black. How can this mass have come out of the black holes? Well, it is perfectly true that black holes are surrounded by a spherical event horizon, and once inside, any material is on a one-way trip to oblivion. But the gravitational waves didn't come out of the black hole, they formed outside the black holes, and they carry away the binding energy of the two black holes. To see what this means, we need to look at analogies from other areas of physics. Stars are powered by converting hydrogen nuclei into helium nuclei. 4 protons are transformed into a helium nucleus, which consists of 2 protons and 2 neutrons. But the mass of a helium nucleus is about 4% less than the mass of the 4 protons. This difference in mass is the binding energy of the helium nucleus, which is released in the form of various particles during the nuclear fusion process, as shown here. This nuclear binding energy is what lights up the Sun and stars. Another example involving much less energy is when a proton and an electron come together to form a hydrogen atom. A well-separated proton and an electron have slightly more mass than a hydrogen atom that will be formed when they combine. The positively charged proton and the negatively charged electron are attracted to each other by the electromagnetic force, and as they approach and form the hydrogen atom, one or more photons are released and they take away the binding energy of the atom. To separate the proton and the electron again, this energy must be put in, and this can happen in various ways when the hydrogen atom interacts with a photon, in a chemical process, or if the hydrogen is heated to several thousand degrees. Now back to the colliding black holes. There is very strong gravitational attraction between the two black holes. The closer they approach each other, the greater the amount of binding energy that is released. And this energy is radiated away in the form of gravitational waves. Consequently, the mass of the bound pair of black holes is less than the total mass of the two black holes when they were well separated. Although the length scales are vastly different, there is a clear parallel between the binary black hole and the hydrogen atom. The hydrogen atom is bound by the electromagnetic force, and the binding energy of the proton and the electron is carried away as electromagnetic waves. Whereas the binary black hole system is bound by gravity, and the binding energy is carried away as gravitational waves. The size of a black hole is determined by its mass and the rate at which it spins. The greater its mass, the greater the size of the event horizon of the black hole. If the Sun collapsed and formed a black hole, its event horizon would have a diameter of just 6 kilometres. The supermassive black hole at the centre of the galaxy is about 4 million times the mass of the Sun. So its event horizon has a diameter of about 24 million kilometres. It would fit inside the orbit of Mercury around the Sun. Now, as time passes, a black hole accumulates material, gas and other material from its surroundings. So its mass increases and therefore the size of its event horizon increases. One way of putting this is to say that the area of a black hole's event horizon increases with time, and this is a very general feature of black holes. Hawking was speculating about what happens when black holes collide well before any firm evidence for the existence of black holes had been discovered. In 1971 he proved a remarkable result about what happens in such an event. When two black holes collide and merge, no matter how fast they are spinning and whatever the details of their encounter, the area of the event horizon of the final black hole must be greater than the total area of the event horizons of the two black holes that collided. Indeed, Hawking showed that in any process whatsoever, according to general relativity, the total area of black hole event horizons can never decrease. This is Hawking's area theorem, a very abstract result proved by Hawking using very sophisticated mathematical techniques. Although it might sound like a quirky fact without much physical significance, it opened the door to a profound re-evaluation of the role of gravity in the universe. It is the key to an astonishing connection between collapsed stars and steam engines. But that is a story for another video. Stephen Hawking was Lucasian Professor of Mathematics at the University of Cambridge from 1978 until his retirement in 2009. This was the position held by Isaac Newton 300 years earlier. Stephen Hawking has now been buried in Westminster Abbey, close to the tomb of Sir Isaac Newton. I hope you enjoyed the video. We'll be exploring Hawking's work further in the near future, so please subscribe to the video channel and I'll look forward to seeing you again soon.